Hi, I'm going to talk about functions of several variables. This is section 14.1 in the Stewart textbook. We'll talk about functions and their domains and ranges and graphs. Then we'll talk about their traces and contour lines, and I'll explain what those are. And then at the end, we'll take a special look at functions of three variables and some of the issues that come up there. For functions of two or more variables, that's what we're talking about. And there's an example written here, which is f of xy equals x plus 2y plus 3. If you input an x and a y, like x equals 1 and y equals 2, then it would output a number. It would output 8. That's a function. This example that's written here is a function of two variables, x and y. In your previous calculus classes, they've focused primarily on functions of one variable, so that's called single variable calculus. They typically have y equals f of x, and you find derivatives and integrals. And now we're going to start looking at functions that have multiple variables. Well, like any function, a fundamental aspect of functions is to look at their domain and range, and that's something we can look at. The domain of any function is the set of all valid inputs to the function, and the range of a function is the set of output values of the function. For instance, with this example that's written here, f of xy equals x plus 2y plus 3, the domain is all of R2, all pairs x and y without restriction. X can be any real number and y can be any real number, and we get a valid expression here. So there's no domain restrictions in this function. The range of this one is all real numbers. Any real number can be gotten as an output. So for example, if you set any target to get a target lambda, this is Greek letter lambda, with lowercase looks like it's written here, and uppercase looks like this, sort of an upside down capital V. To get any target lambda, so lambda is a target real number, and I'm claiming that in my range I can get all real numbers. So you can set any target you want, and I need to fill in an x and a y that will hit that lambda, and I can do it. We could say put lambda minus 3 for the x and 0 for the y, right? Because then f of lambda minus 3, 0 would be lambda minus 3 plus 2 times 0 plus 3, and we get lambda. And there's many other xy's that also work. But for right now, if we're talking about range, the question is just, can you hit it? And the answer is yes, in at least one way. Here's another example, f of xy. So again, a function of two variables, like the previous example. And this time, f of xy is x plus y divided by x minus y. So what are the domain and range for this example? Well, the domain is the set of x's and y's that are valid inputs, and it's not a valid input if we're dividing by 0. So the domain is the domain restriction is just that x can't be equal to y. We can't divide by 0, so x minus y can't be equal to 0, and that just simplifies into x can't be equal to y. Now, the official mathematical notation for this is to take the set of pairs xy in R2. This bar means such that, and then x is not equal to y. So the set of pairs xy in R2 such that x is not equal to y. And that's what these symbols stand for, and that would be the official mathematical notation for this domain set. But to tell you the truth, unless you're writing some formal official mathematical text or something, if you just say the domain is the set where x is not equal to y, that will convey the idea pretty clearly. Well, I guess I should say that some professors are going to be a little bit pickier than I am, and so you might have other professors who want you to write using proper notation, but well, so if you run into them, then here's the notation and you can use it. But for right now, we're more worried about just the idea and the concept and understanding the idea of it. What about the range of this one? The range is a little bit trickier problem. So I would invite you, if you're curious, to pause the video for a minute and think about it. What possible outputs can you get from this expression? Can you find an x and a y that make this equal to 10? Can you find an x and a y that make this equal to 0 without dividing by 0? Can you find an x and a y that make this equal to 275? All right, so the answer is that the range is all of R. The range is all real numbers. Every real number can be made as an output of this function. So there's a second puzzle for you. Can you figure out how to do it? If I give you a target like -1 or 13.2, can you find an x and a y that give you that value? Here's one way. I think that there are many solutions. There's infinitely many solutions, but it's not super obvious how to come up with them. So here's one possible way. Given any target lambda, we could set x to be lambda plus 1 and y to be lambda minus 1. And that works out. When we do x plus y, lambda plus 1 plus lambda minus 1 is 2 lambda. And when we subtract them, lambda plus 1 minus lambda minus 1 is 2. And 2 lambda divided by 2 is lambda. And there's no division by 0 here. So for any lambda, this will work. And I'm curious to hear if you came up with a different solution. Let me know. Now, having talked about the domain and range and shown a couple of examples, I should say that the domain is really important and has to be considered with many different functions. The domain issues come up. The range is a little bit less central and doesn't get mentioned very often, or at least not in Math 275. So if you focus on the domain. One more important thing about functions is their graphs. Every function has a graph. So for a function f from R2 to R, this is function notation. What it means is that f is a function from R2 to R. So the inputs are taken from R2. So in this case, we would have x, y's as our inputs, and it's a function to R, meaning the outputs are in R. So this function f, you input an xy pair, of real numbers, and it outputs a number. So that's what this notation means. F is a function from R2 to R. It inputs a pair xy and it outputs a single number. And so if you wanted some terminology for this, I would say that this is a scalar function, as opposed to the, in contrast to the last chapter we looked at that had vector functions where it outputted a vector. This one is a scalar function because it's outputting a scalar. And this function here is a multivariable function because the inputs have two variables, x and y. So this function f is a multivariable scalar function. All right, anytime you have a function like that, a multivariable scalar function, the graph of that function is the set of x, y, z's in R3 that satisfies z equals f of xy. So in other words, for each x and y, we take the x and the y as our x and y coordinates. Those are the inputs. And then we take the output of the function to be the z coordinate, or the height of that point. So the graph is just that collection of dots, which is typically going to be infinitely many dots, and we just draw it as a surface. All those points taken together. It's defined, the graph is defined by an equation. It's just the equation z equals f of xy. Later on, we'll talk about parametrization of surfaces in chapter 16. So that's coming a little while later. We'll have parameterized surfaces, and these graphs have a parametrization. And when we come to it in chapter 16, I'll explain what this means and what it's useful for. But perhaps it's reminiscent of something we said, that for a line, we can have a parameterization of a line, but we could also write equations of the line. For planes, we talked about equations of planes, and I believe I mentioned that there are parameterizations, we just didn't talk about them yet. And now for graphs also, we have an equation, and later on we'll talk about a parameterization. Here's an example. The multivariable scalar function that was on a previous slide is f of xy equals x plus 2y plus 3. What does that graph look like? Well, it's given by the equation x plus 2y plus 3 equals z. And x plus 2y plus 3 equals z, that equation defines a plane because it's a linear equation with a constant. So that defines a plane. And just as a matter of review, do you know the normal vector of that plane? The normal vector of this plane is 1, 2, minus 1. I hope you didn't think that it was 1, 2, 1. Remember, we have to read off the normal vector, we have to have the x, y, and z all on the same side of the equation. So we would rewrite this as x plus 2y minus z equals minus 3. And then that would give us our normal vector, and that's where the minus 1 comes from. Well, that was just reviewing something about planes. The point is more that this graph, we can write down the equation of it, and in this case we can recognize what the equation is. It's the equation of a plane. What does a graph look like for the function f of xy equals x? Is it a line in the xy plane? Is it a line in 3 dimensions? Is it a horizontal plane, or is it a tilted plane? The answer is D. It's a tilted plane. The graph is given by the equation z equals x, or in other words, x minus z equals 0. Or in other words, 1x plus 0y minus 1z equals 0. So this is a plane with a normal vector given by 1, 0, minus 1. So it's a tilted plane. It's not horizontal because the normal vector doesn't point straight up or down.